All right, today we're going to continue on with more extrema, and today's going to be about monotonic functions. I'm skipping over 4.2. I just think for the flow of the course, it makes sense to jump over it, and we'll come back to it in a little bit. But I think you'll see once we go back to it why I choose to skip it initially. So we've already talked about maximum and minimums. So let's say you've got this function, x to the fourth plus 2x cubed minus 2x squared. Inner interval is negative 3 to 1. Already got the derivative, which would just be from power rule. You could find the critical points by setting the derivative equal to 0. And then you'd be able to factor out a 2x and then factor the remaining binomial. So the question then becomes, how do you know if your critical point, which remember critical points are where is the function 0 or undefined, how do you know it's a local max, a local min, or what if it's just neither? What if it just happens to be a place like we talked about with x cubed where the derivative is equal to 0, but it goes from increasing, it stops at 0, and then goes right back to increasing again. So the problem is, I know these values, but they don't really tell me anything on is it a max or a min. Because if I look at negative 2, I'm at negative 8. If I look at 0, I'm at 0. 1 half, negative 3/16, negative 3, 9, and then 1 is at 1. So you have your endpoints and your critical points. Now I will pull up the graph in a second. You can go, oh, well, that's clearly a max and that's a min. But I do want to do one thing here to show. Think about any time, or look at our function. It's a polynomial, and this isn't always going to be a polynomial, but for this case, just kind of think back to when you were discussing, well, when is the function positive? When is it negative? When is it 0? Because our derivative's a polynomial, we can kind of, I'm going to kind of introduce the idea with the idea of polynomials and roots. So let's break this function up by its roots. So negative 2, 0, and 1 half. And these would keep going to the left and right. Now what I'm going to do is I want to pick points that are in between. So here I'm going to pick x equals negative 1. Here I'll go with x equals 1/4. Now, because of this being 1, I'm going to pick x equals 3/4 and not go with 1. And then here I'm going to go with x is negative 2.5. Again, because our interval is limited to negative 3 and 1. And if we take our function, which we know is going to be, so if we take the derivative f prime of x, that's equal to, if I factor out a 2x, I get 2x times 2x squared. I just have to write it correctly. Plus 3x minus 2. Which then we'll factor one more time into 2x times 2x plus 1, or sorry, 2x minus 1, and x plus 2. Now, you might be looking at that going, okay, why would you pick that? So let's start with f prime of negative 1. Now, I don't have a calculator handy right now, so this is part of the reason I'm factoring it. If you do have a calculator, the nice thing is you just kind of plug in these in-between values, and here's all you care about. So I know if I plug in negative 1, this is going to become some negative value. 2 times negative 1 minus 1 is also going to be a negative value. And then negative 1 plus 2 is a positive value. So I have a negative times a positive, which means that this is positive. So between negative 2 and 0, it's positive, which we're going to say means the function is increasing, because remember, this is the derivative. So this means the function is always increasing between negative 2 and 0. Plug in negative 2.5. This will be negative. And again, I don't care what the value is. All I care about is the sign positive or negative? Plug in negative 2.5 into here, also negative, and then also negative. Negative times a negative is positive, times another negative is negative. So I know the function is decreasing on that interval. And just to save some time, at 1/4, this is going to become negative. And then at 3/4, this will be positive. And so what you notice is it goes decreasing, increasing, decreasing, increasing. So if I'm increasing and then decreasing, this is going to do something like this, which would give you a max. If I go from decreasing to increasing, it does something like this, and I get a minimum. Now, this is where you have to be careful when reading it. Let's go back to the endpoints here for a brief moment. So I have negative 3, 9. And then I also have 1, 1. So this is how you have to read it for the endpoints. I'm decreasing from negative 3, 9 down to negative 2, negative 8. That's going to make this, because I'm decreasing from a point, that makes this a max. Because if you're starting at the left, yeah, it's a left endpoint. So if it's always decreasing from that point onward, that has to be a max. And then if I'm increasing to this point on the right, that means it has to be a max as well. Because if you're increasing towards a point, that makes it a max. If you're decreasing towards the point, that makes it a min. And notice the difference. From the left, it's I'm decreasing from the point, negative 3, 9. On the right, I'm increasing to the point 1, 1. So, and it is a little bit easier to tell because going from 9 to negative 8, that would have to make 9 is a max, negative 8 is a min. But this is just kind of the thought process behind how you come up with these and determine Is it a max? Is it a min? Is it neither? So this is a formal way of saying what I was just talking about with the function. So if a function is defined on an interval, so let f be a function defined on an interval, and let x1 and x2 be any 2 points in it. If f of x1 is less than f of x2, whenever x1 is less than x2, then it's said to be increasing. So that's like going from here to here. Here's x1, here's x2. And then opposite, if you start here and then decrease to here, that would be decreasing. Now, we classify a function that is always increasing on an interval or always decreasing on an interval to be called a monotonic function. So if you think monotone, like monotone voice, mono, one, it has one direction. Now, if you think monotone voice, we think somebody very boring. Their voice does not change. It's very flat. When we talk about a monotonic function, we're talking about it's always going up or it's always coming down. Something like that. So that's how you need to associate monotonic is with increasing and decreasing. So like if you take this function, x times sine of x, is it monotonic from -5 to -3? So I'm just going to mark each one of these with a color. So here's -5. So -5, -4, there's -3. So is it monotonic? Yes. It's always increasing. So we would say that function is monotonic on that interval. How about if we check from 2 to 4? So here's y equals 2. And then down here is y equals 4. I would say yes because it's increasing, or it's decreasing. Now what if we look at -1 to 1? Here's -1. There's +1. And you can see the issue here. We're decreasing until 0, at which point this function becomes increasing. So no. And the reason, it goes from increasing to decreasing. Or sorry. Let me say it the correct way. It goes from decreasing to increasing. So what about from 5 to 9? Starting to run out of colors to use. Well, legible ones. Would legible be the right word for a color? So 5, so then 6, 7, 8, 9. That's definitely a no. And again, increasing to decreasing. And this time I'm actually going to write it correctly. So one last one, -8 to -6. So there's -5. So here's -6, -7, -8. Not quite there. But yeah. That one would be a yes. because this would be an always decreasing. So monotonic simply means the function's always increasing or the function's always decreasing. And there's not like a special name where it goes like increasing to decreasing, decreasing to increasing. We just say it's not monotonic or a non-monotonic function. So like x cubed is a monotonic function because it's always increasing. Except when you hit 0. And then, so it increases from negative infinity to 0, and then from 0 to infinity. It only has one point where it's not increasing, and that's where the derivative is 0. So to go on, the first derivative test is a way to test for monotonicity, or just to test to see if it's a monotonic function. And this is where you have to be careful with some definitions. Suppose that f is continuous on the closed interval AB, and it's differentiable at the open interval AB. So it only has to be differentiable on the interior, but it has to be continuous to the exterior. That's what you would think about that as. So if f prime of x is always positive for every point in your open interval, then that means it's increasing on the entire closed interval, and then vice versa, which makes sense. Derivative is a rate of change, so if the function is always increasing in an interval, or if the the derivative is always positive in an interval, that means the slope is positive, which means the function's increasing. And again, vice versa for decreasing. So here's the function x cubed minus 3x. And you can see the green is the derivative, which would be 3x squared minus 3, or just 3 times x squared minus 1. And then look at the roots of this derivative. The roots of this are 1 and negative 1, which finding the roots of this are the same as saying where does it equal to 0. And you can see where the derivative is positive, then the function is increasing. Where the function is, or where the derivative is negative, the function's always decreasing. And so this is why we use the continuity part, or this is why it's nice for differentiable functions. If they're continuous on that interval and differentiable on the open interval, then we can actually start to talk about these functions in some interesting ways. So one thing you have to start kind of working with is the idea that typically we've talked about if the function is differentiable, then it's continuous. Well, what about the continuity of the derivative itself? That's where you have to be careful. And this is what we did before. F prime of x can only change signs at a 0. And those zeros of the derivative will divide the axis into monotonic intervals. This is just kind of formalizing that idea where I talked about, like, just treat it like roots of a polynomial. This is the formalization of that. Now, specifically here, it says f prime is continuous. Eventually, we're going to also bring in that it has to be just basically defined on the interval. So when you work with it, you can also use where's the function's derivative equal to 0, or where is it undefined. We're going to bring both of those into account. Now, the key thing is you're not going to have an extrema where a function is increasing or decreasing. This is why in those intervals, we always said, like, even if I pick like this point, I can say, well, if I look to the left or to the right, there's always a larger or a smaller value. That's why you need that's why the intervals of increasing and decreasing are important. Now, you do have to be careful of, are you on a closed interval? Because if you're on the closed interval, like the previous one where it was -1 to or -3 to 1, then you had to take into account some other values and look at the endpoints. The endpoints are the only exception of the intervals of increasing or decreasing. So here's a monotonic function, or here's a function that's increasing after a point where it's decreasing. I should have said that backwards. It goes from decreasing to increasing. So again, not all functions are always going to be monotonic. Most functions are not monotonic. You have very few things like an exponential function. Think about your trig functions. They're not. Y equals x. X cubed is a little fishy because it does have that point where the derivative is 0. So it goes increasing, stops at exactly 1 point, and then goes back to increasing. But most of the time, you want to assume the function is differentiable. So since there are points where the derivative is positive, and there are points where the derivative is negative, there's got to be at least 1 point where the derivative is 0. And remember, those are our critical points of the equation. So, like this function, it goes from decreasing to increasing. So we know somewhere in between there, it has to have a critical point, which is where the function was, or the derivative was equal to 0 or was undefined, or the endpoints. But at this point, there's got to be at least 1 point where the derivative is 0, since it's got to go from increasing to decreasing, or vice versa. So take something like 3x squared minus 12 as the derivative of x cubed minus 12x minus 5 on the interval -3 to 3. Go back to intermediate value theorem, Darbo's theorem, stuff like that. And if you notice, this is one of those cases where picking a point or checking the endpoints isn't a good idea. Because remember, part of what we would do is we would say, okay, if the function is differentiable, then I'm going to take it, or I'm going to take the derivative at the endpoints, and I'm going to say, okay, if one goes from positive to negative or negative to positive, then that means at some point this function had to change directions. But this is a case where you don't actually get it to work, because at the endpoints, the derivative's the same. It's positive, so the function does not guarantee anything, or that theorem does not guarantee anything. So you just got, so if you look at that initially, you go, okay, well, is the function always increasing because I checked the two endpoints and it was positive at both of them? Heck, at this point, it was also the same value. No. It just so happens to be that they have the same slope here. So here's at -3, and here's at +3. So all that means really is that their tangent lines are parallel. But it goes from increasing to decreasing to increasing. So you have to be careful. Just because the derivative is positive at 2 points doesn't make a function monotonic. This is why I say check roots, check where the derivative equals 0. Because you can see if we set this one equal to 0, then we get 3x squared equals 12. X squared equals 4. So thus x is equal to positive -2. which if you look, lo and behold, positive and negative 2 just happen to be where we go from increasing to decreasing. So if I picked a point like x equals 0, like say you don't have the graph, you can pick points like that, and you can see that there are intervals that are increasing, those being negative infinity to negative 2, and from 2 to positive infinity. But there is an increasing interval, or a decreasing interval, sorry, of negative 2 to 2. So you have to be very careful on those. Don't just jump to the conclusion that I checked these 2 points, they were both positive, so it's monotonically increasing, or I checked these 2 points, they're both negative, so it's monotonically decreasing. You have to check the derivative at the places where it's equal to 0 and undefined. That's going to be your key takeaways. So our critical points, that's what I literally just said. I know what I'm going to say before I even say it. The critical points, which is where the derivative is equal to 0 or undefined, are the places that we're going to break the axis up. And it breaks that up into monotonic pieces, or monotonic intervals. Let me be slightly more mathematical about it. So, the first derivative test, and this one's pretty straightforward. This one's kind of what I said. If the derivative changes from negative to positive, which means decreasing to increasing, then f has a local minimum at the point where that change happens. If it goes from positive to negative, which means increasing to decreasing, then it's going to have a local maximum at the point where that occurs. If it does not change signs, then there's no, or if the derivative does not change signs at c, which means it's both positive or both negative, then there's no local extrema there. Extremum is the singular, extrema is the plural at the point C. So like if you notice this point C1, we are positive slope. So we go increasing, take a quick break, and then go increasing again. So derivative does not change. It only is equal to 0 at one point. Versus we go increasing to decreasing. So that goes from positive to negative. So that answers 2. That's why it's a local max. This one goes from decreasing to increasing. So that makes C3 a local min. Now C4 is a special case because it's increasing, undefined, but then decreasing. And notice it's not the function is undefined at C4, it's that the derivative is undefined. So the function being defined and making a cusp, a corner, something like that is okay. But the nice thing here in the takeaway is we go from increasing to decreasing on a continuous function. If this function was not continuous, then answers are null and void. You have to have a continuous function because otherwise I could do this. This goes from decreasing to increasing, but it's not continuous. So how do you classify it? And then the last one, at C5, you go from decreasing to decreasing. So again, decreasing, break, decreasing, not an extrema. So just be aware, if the derivative changes from positive to negative, negative to positive, then you're going to have a local max or min. If it does not change, but it hits 0, so it goes positive, 0, positive, or negative, 0, negative, those are places where they are critical points because they are where the derivative is equal to 0, but they're not an extrema. So just be aware of that. This is always an interesting example. So notice this is the derivative of the function. You don't have what the original function is. But first we need to identify what are your critical points. Remember, critical points are where is the function's derivative equal to 0 or undefined. So if we look at the numerator of this function, then I have positive 2 and negative 4. These are where f prime is equal to 0. But then look at the denominator. I have negative 1 and positive 3. This is where the derivative is undefined. So now if we need to identify the intervals of increasing and decreasing, here's what I like to do. Now some people will draw a box. I just prefer to have a line, just because I can think about it as just like the x-axis. And what I tend to do is, so 2 and negative 4 are going to be solid lines. So here's negative 4, and I'll put positive 2 right there. But now f prime of x being undefined, think about when we do undefined, that's usually a vertical asymptote. So that's what I'm going to use to represent it here. I'm just going to draw a little dashed line. And that's going to give me my partitioning into these intervals of increasing and decreasing. So now this is where you just plug in those in-between values. This is why I say I really only care if they are positive or negative. So I'm going to pick easy points. If you can, always pick easy points. So like here, I have to do x equals 2.5. I could do x equals 2.1, 2.01, but I'm just going to do 2.5 because it's in the middle and it makes life a little bit easier. But like for this one, x equals 4. Don't pick something weird like pi or 3 pi. Just pick integers. It'll make your life a lot easier. So like here, negative 2, and then here, negative 5. So if we plug these in, so I'll do that for the first one. So f prime of negative 5. So that's going to give me a negative value, another negative value, another negative value, and another negative value. So 4 negatives makes a positive. So I know it's increasing from negative infinity to negative 4. Now let's check negative 2. So negative 2 minus 2, that's a negative number. Negative 2 minus 4, that's a positive number. Negative 2 plus 4. Negative 2 plus 1, that's a negative. And then negative 2 minus 3, that's also negative. So 3 negatives and a positive makes a negative. So then this is going to be decreasing from negative 4 to negative 1. Now I'm just going to talk through the rest of them because the rest of them are just same idea. Plug in the values. So this one's actually nice. Negative. So if I plug in 0, I get negative 2, positive 4, positive 1, and negative 3. I don't care about the value. I just care that I have 2 negatives and 2 positives, which means I have a positive. So I know that it's increasing from negative 1 to 2. So then if I plug in 2.5, I'm going to get positive for the first term, because this would be, in the order I'm reading, I'm just reading just like a typewriter. It's left to right, go down, left to right. So plugging in 2.5, I would get a positive, positive, but then a negative. And so then another interval of decreasing from 2 to 3. And so then if you plug in 4, positive, 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 positive. So then from 3 to infinity, it would be positive. So our intervals of increasing, I'll write first. That's going to be from negative infinity to negative 4. If I can write the number 4. So it's negative infinity to negative 4. Union, because we're putting all these together. Negative 1 to 2. And then I said that would be positive. So then lastly, union 3 to infinity. And then decreasing is going to be all the leftover intervals. So negative 4 to negative 1, union 2 to 3. And if you notice, all of your intervals should be taken into account. There's very few cases, and I mean very, very few, where you're going to have like an interval where nothing happens. And here's one trap that I don't want you to fall into. A very common mistake is to first look at these and go, oh, it goes positive, negative, and then a positive again. So they must alternate. Not necessarily. Think about like multiplicities of functions. If you have times where maybe a value is cubed or squared, that could change the value of the function. So just keep those in mind. You don't want to accidentally trick yourself into a false idea. Always plug in the values to make sure of what it's going to be. So where is it going to have local? We'll start with maximums again. So we'll have a maximum at x equals. Remember, a max is where it goes increasing to decreasing. So it goes from positive to negative. So that's at negative 4. Because we go plus to minus. And then also at 2, because we go plus to minus. And so then we're going to have a minimum at x equals negative 1, because we go decreasing to increasing here. So negative 1. And then from decreasing to increasing at 3. Now, this is one thing to be aware of. We don't necessarily know from this function if we're actually going to have them at negative 1 and at 3, because that's where the derivative is undefined. Just because the derivative is undefined does not necessarily mean that the function is undefined there. So based on our values and the fact we go increasing, decreasing, decreasing, increasing, that's our assumption. So here's the graph of f prime. And here's the graph of f. So in reality, notice we said that we had to be careful because just because the derivative was undefined, we didn't necessarily know if the function was. But now if you look at the points -1, which is here, that looks like a vertical asymptote. Maybe it does go down to a value. I don't know. But it does not look like it from there. So from the way that looks, we might can actually strike through -1. And then if we look at +3, so 1, 2, 3, also can strike through that one as well. Because these are places where the derivative was undefined. So technically don't actually know. Because you got to assume that these are going to keep going. Same way that you don't say, oh yeah, that just stops there. This is a snapshot of the function. So unless you know the original function, you can only make your guesses and your propositions based on what you have. So in this case, we only had the derivative to go off of. We don't have the original function. And when you look at the original function, you can go, oh, well, maybe, well, it's clear that that function is not defined at -1 or 3. So I can rule those out as being a local max or min. And so that's 4.3. Next, we're going to look at 4.4. And this is going to deal a lot with second derivatives. And how do we use second derivatives to determine maxes and mins and things like that?